All right, welcome to improper integrals. Now, what's an improper integral? An improper integral is basically, one definition is when you have an integral where one of your boundaries or both of your boundaries have an infinity in them. So when your limit of integration has an infinity, either the top, the bottom, or both, that's an improper integral. Now, why is this improper? Well, the reason is when you think about the fundamental theorem of calculus, the fundamental theorem of calculus is the theorem that said basically if you want to integrate the integral from a to b of f of x dx, you do f of b minus f of a, where f prime equals f. In other words, you take the antiderivative, plug in the bounds, and subtract. However, this is only defined where a and b are constants. Well, if we look at these integrals here, the limits of integration aren't both constant. A is a constant, but infinity is a concept. It's an idea. It's not an actual constant. So what we do to kind of sidestep that problem is we say, you know what, let's call this infinity b and take the limit as b approaches infinity. So as b is a growing constant headed toward infinity, then we're going to evaluate the limit of f of x from a to b. Conversely, we say, you know what, if I have a, I can have a lower limit of negative infinity, call that a. And if there's two infinities, we can split it at somewhere in between, say 0, 1, 75, whatever you want. Split your integrals in between, have two separate integrals, and make both of these limits. All right? Honest to goodness, it's really not that difficult. It's just an extra step of putting in a limit. So let's say I have the limit from negative infinity to 0 of e to the x dx. So the first thing we're going to do is say, wait a minute, I can't have a negative infinity here, so we're going to rewrite it as the limit is a approaches negative infinity from a to 0 of e to the x dx. Now I evaluate this limit. Take the antiderivative, well, e to the x has an antiderivative of e to the x, from a to 0, and I'm still taking the limit as a approaches negative infinity. And that's going to be e to the 0 minus minus e to the a. And again, as a approaches negative infinity. So now finally, as a approaches negative infinity, I have e to the 0, which is 1, minus e to the negative infinity. Well, what's e to the negative infinity? That's the same as 1 over e to the infinity, which is 1 over infinity, which is 0. 1 minus 0 is 1. So the integral from negative infinity to 0 of e to the x, dx is 1. So you might be thinking, okay, fantastic, whatever, I got an answer. Well, let's think about that answer for a minute, and this is where I like to freak everybody out. So here is the x-axis, whoop, here is the x-axis, here is the y-axis, and here's the graph of e to the x. If I take that and I think about what this integral represents, one interpretation of an integral is it's the area underneath e to the x and above the x-axis from negative infinity to 0. Well, here's e to the x, here's the area from 0 to negative infinity. And I could keep shading and shading and shading and never stop. Yet the answer to the integral is 1. In other words, even though you'd be shading until the day you die, you pass it in your will to your children who would pass it to their children, and everyone would shade forever, that area approaches 1. Even though it keeps growing, it grows with a limiting value of 1. Kind of cool that you have what looks like infinite area, and it's not actually infinite. So let's do 1 to infinity of 1 over x dx. This time I'm going to draw the graph first. So here's 1 over x. Here's the area from 1 to infinity. It's going to be all this stuff. To figure out if that area is finite or infinite, the first thing I'm going to do is say I'm going to take the limit as b approaches infinity from negative 1 to b, positive 1 to b of 1 over x dx. The antiderivative of 1 over x is ln absolute value of x from 1 to b as b approaches infinity. which is going to make this the limit as b approaches infinity of ln b minus ln 1, which is going to become, if b is going to infinity, ln infinity minus ln 1, which is infinity minus 0, which is infinity. Wait a minute. How could this area be 1, but this area be infinite? Honestly, just 'cause. What really happens here is that e to the x is approaching the x-axis very, very quickly, whereas 1 over x is not approaching the x-axis that quickly. So all of this area here just keeps basically adding additional decimal places in a way. So I have, maybe the area from here to here is like 0.9, and then I add in this stuff, and now I'm at 0.99, 0.999, 0.9999, 0.99999, and then we get to 1. Whereas here, this area might be 0.5, and this area right here might be 0.4, 0.3, 0.2, 0.1, 0.09. The area is growing a lot faster because there's a lot of small values, but there's tons of them. Whereas here, there's a lot of small values, but the values are so small that they don't combine to go to infinity. Long story short, though, honestly, if you just know how to evaluate the limit, your answer will expose itself very quickly. One more thing I want to say about this infinity. Sometimes when we have an improper integral that goes to infinity, we'd like to say it diverges, meaning it doesn't converge to a value, it diverges toward infinity. All right, turn the page. Next example. Our next example, we have the integral from negative infinity to infinity of this guy right here. And it's that graph, so I'd be finding all this area right here, seeing if it's finite or infinite. So this is one of those where I have a double infinity, so I want to split it up. So if I split this up, I'd have the integral from negative infinity to 0 of dx over 1 plus x squared, plus the integral from 0 to infinity of dx over 1 plus x squared. Now, this function is even, and I'd really prefer not to have two separate integrals. So since it's even, and only because it's even, I can double the integral from 0 to infinity to get the whole thing. All right, well, I have an infinite limit. I'm not supposed to have an infinite limit of integration, so this is going to be 2 times the limit as b approaches infinity from 0 to b of dx over 1 plus x squared. Now I'm going to take the antiderivative. What's the antiderivative of dx over 1 plus x squared? Yes, you need to have these memorized. Think. 1 over 1 plus x squared. That's the derivative, if I could talk. That's the derivative of inverse tan. So I have inverse tan x from 0 to b. The limit as b approaches infinity, and I'm doubling that. So it's going to be 2 times the inverse tan of b minus the inverse tan of 0. And I forgot to write in my limit here. Limit as b approaches infinity. So I have 2 times inverse tan infinity minus inverse tan 0. Okay, inverse tan infinity, inverse tan 0. Let's think about that for a second. Well, here's the graph of tan x from negative pi over 2 to pi over 2. Where on this interval does tangent go toward infinity? It does that at pi over 2. Where does tan equal 0? It equals 0 at 0 times 2 equals pi. So this area right here is pi. All right. Now we're going to start the next one. Don't let the skull and crossbones scare you. It's not that bad. Actually, I'm lying. It is that bad, but just be ready. All right, hold on. Landon wants to tell everybody a joke. Here you go, Landon.
No, I don't.
He doesn't remember the joke. You know your joke. Can you do it?
What was 6 afraid of 7? 7, 8, 9.
All right. Now that you got a joke, let's come down here to this one. Ooh, skull and crossbones and a smiley face. You know this is going to be good. So, if you want to evaluate this integral, first, on first glance, really, nothing terrible. X times e to the negative x dx. Okay, fine. So we're going to take the limit as b approaches infinity from 1 to b of x e to the negative x dx. All right, what's the antiderivative of x e to the negative x? Yeah, I don't know either. So I have a product I can't get rid of. All right, let's try a u sub. Yeah, that's not going to work because u would just be negative x. That doesn't help me. But if a u sub doesn't work and you have a product you can't get rid of, you're going to do integration by parts. So u, du, dv, and v. So LIATE, algebraic, I'm going to let u equal x, du is dx, dv is everything else, e to the negative x dx, and the antiderivative is negative e to the negative x. So on this one, we're going to rewrite the integral of x e to the negative x dx as u times v minus the integral of v du. And that's going to turn into negative x e to the negative x minus e to the negative x plus c. Well, I wasn't trying to evaluate an indefinite integral. I was trying to evaluate a definite integral. So the integral from 1 to b of x e to the negative x is going to be u, not u, what am I saying? It's going to be this antiderivative here evaluated from 1 to b as b approaches infinity. So I have the limit as b approaches infinity of negative b e to the b minus e to the negative b minus what I plug in when I get 1. So minus negative 1 e to the first minus e to the negative 1. Okay, now I'm going to plug the infinity in. So negative infinity e to the infinity minus e to the negative infinity minus negative e minus 1 over e. Okay, hang on, Mrs. Vibber thinks I made a boo-boo. Oh, I knew where I made my boo-boo. This should be an e to the negative x. I lost a negative sign. I knew that was supposed to be there. Sorry, this was a negative sign, which means that was a negative b, which means this is a negative infinity. There we go. So, now I have to evaluate this. Negative infinity times e to the negative infinity, which is 1 over e to the infinity, minus 1 over e to the infinity, technically plus e plus 1 over e. Well, this is going to be infinity, negative infinity, times 0 minus 0 plus e plus 1 over e. This is indeterminate. So not only did we have to do integration by parts this time, and we had to do the limit thing, now I have to do L'Hopital's rule. Alright, and you know what? Did I lose another negative sign? Hang on, before I start L'Hopital, I lost another negative, didn't I? This was e to the negative x, so this should be e to the negative 1, pardon me. So these should be both 1 over e's. Pardon me, so this should be 2 over e. Sorry, that was just simple, quick mistake as I was putzing with my computer. Sorry. So anyways, we're back to this. I have negative infinity times 0, which is indeterminate. So now I have to remember that I'm taking the limit as b approaches infinity of negative b e to the negative b, which is the same as the limit as b approaches infinity of negative b over e to the b. And let's see, as b goes to infinity, that's infinity over infinity. So now I can do L'Hopital. The limit as b approaches infinity of the derivative of each, negative 1 over e to the b. Now as b goes to infinity, that's negative 1 over infinity, which is 0. So this indeterminate form is actually just 0 because of what we just did, which means I have 0 minus 0 plus, that's not supposed to be there anymore, 2 over e, which is 2 over e. Holy cow, that was fun. The only thing that would have made that better if there was a logarithm, and there's no logarithm, I'll have to deal with my exponentials, but hey, not so bad. I apologize for my tiny mistake in here, but there you go. Those are limits with infinite bounds. Come on back for more.